everyone. Hi, I'm Marzia. I'm a research scientist at Cohere for AI. And welcome to the C4AI Fireside Chat. This is a seminar series where we focus on people and we bring together leading researchers as well as rising stars in machine learning to discuss their research journey and share their insight with young researchers. Today, we have a very special guest, and I'm very excited to introduce one of the leading researchers in AI, Professor Max Welling. At least I'm going to try to introduce because I think everyone knows who he is. Max is a full professor and research chair at University of Amsterdam and American distinguished visiting professor at Caltech. He co-founded QUVA to build a platform for next generation materials to tackle global sustainability and clean energy challenges. He is a fellow at the Canadian Institute for Advanced Research and the European Lab for Learning and Intelligent Systems, ELLIS, where he served on the founding board. His previous appointments include partner and VP at Microsoft Research, VP at Qualcomm Technologies, professor at UC Irvine, a postdoc at UCL and University of Toronto, and postdoc at Caltech. He finished his PhD in theoretical high energy physics under the supervision of Nobel laureate, Professor Gerard, Hooft, and in the last 3 decades, he has published many influential papers. I don't think I have to name all of them, but everyone knows that. And he has won several awards, including multiple Test of Time awards at ICLR and ICML, which is a testament of his influence in this field. Welcome, Max.
Thank you very much, Marzia. Nice to be here.
Great. Thanks for joining me. And for the new people joining, feel free to ask questions in the chat, and I'll hope to get through them today. All right. So I want to ask my first question about your career journey, Max. Can you tell us about what has it been like, and what events and choices do you think were really pivotal to get you to where you are right now?
Yeah, I've made a lot of different career choices actually, and changed quite a bit during my career. It started, I think, when I finished my PhD in theoretical physics. So this was a highly theoretical PhD in quantum gravity. So at that point, I decided I didn't want to do this all my life because it was writing papers, and it's hard to see how that would make a real impact in the world. And so I decided to move to a different sort of younger field where more was going on. I wanted actually to go to theoretical neuroscience, but that became first computer vision at Caltech when I joined Pietro Perona's lab, and then slowly migrated to machine learning, and then did a postdoc with Geoffrey Hinton, first at University College London in the Gatsby unit, and then when he moved to Toronto, I moved with him and did another 2 years there working with him. And so I like machine learning, and so I joined the faculty of UC Irvine for 10 years, after which in 2013 I moved to the Netherlands, became full professor there in machine learning. But then I also wanted to explore the commercial side. So I started the startup with a bunch of friends and students actually. And so I did, I guess, 4 years got involved as a co-founder in this startup CIFAR. That got acquired in 2017 by Qualcomm at that point, who then started their Qualcomm AI Research Lab in Amsterdam, and I joined them as a VP to start that effort. Did that for 4 years, and then I actually wanted to do a startup at that point already. I wanted to go to AI for science, but then I got a call from Microsoft that they started a AI for Science research lab in Amsterdam, and that was too good to ignore. And so I helped found that lab in Amsterdam. And after 2 years, I went back to starting a startup. So I got together with Chad Edwards, who is my co-founder for my current startup called QUVA, who is using AI to accelerate and improve materials design. And in particular, I wanted to work on something meaningful. So we work on carbon capture, so improving materials for carbon capture. So we recently raised 30 million to build that company. We are in the process of building the team, and in September we'll start in full swing and start to actually design new materials using AI. So very excited about that too.
Yeah, thanks. That sounds very exciting. I was wondering, so just how, like, what do you think? I mean, it's kind of clear why it's important to work on this area of using AI for good, essentially how we can help humanity. But what do you think would be what's the main like big question here that you want to study, and why it's important to do that right now?
Yeah, yeah, great question. So first of all, I think humanity has this interesting but somewhat sad feature that we only get to action when things are really dire. Right? We saw this at COVID. It had to get really bad before people got, sprang into action and started doing things, and then we were really good, as a species to do something. Now the thing with carbon emissions and climate change is that everybody knows it's there, but it's again very hard to really take it seriously until it's really in your face. And so we are seeing the effects of climate change, but apparently it's not bad enough for the whole of humanity to really start acting. We are still emitting more carbon than ever before. It's still going up globally, although in the developed nations like Europe and US, it's starting to come down. But we have about 4 years left of space in our atmosphere to emit carbon at the current rate. And so we're not acting fast enough. And I can just clearly see this. And so I think this is one of the most urgent problems to solve at this point. And the interesting thing is that despite a lot of talk about the dangers of AI, which, to more or less degree, I agree with, this is a place where AI can really be applied for good. So, you can really point this AI gun that we have developed and really help solve this really important problem. And so that's why I think this is a really important problem. And it's also very interesting because you can align, doing fantastic and interesting research in AI, at the very frontier of AI, with something that is good for society, but it's also equally interesting as the training large language models. And it's also, commercially interesting, right? I think it's very important to align the sort of commercial interests of sort of a company, because companies make money and those are the real vehicles to make big impact, with something that's good for society. So that's what I've been contemplating, and I think this is the right application for applying AI for good.
Yeah, I definitely see where you're coming from. And from my understanding, one of the main goals of CUSP AI is to explore new ways of combining molecules to address this, like the carbon capture. And one of the main challenges there has been that it's very computationally expensive to explore. And you just mentioned about doing AI research at this frontier. And I'm wondering what types of topics are there other than this just exploration of a huge space?
Yeah. So, for instance, you mean like within the space of carbon, materials design, right? So, what other interesting machine learning tools can you develop for this? There's a few. So, one of them is generative models. So, we all are impressed by all these videos that are being generated by OpenAI of dogs playing in the snow and other very impressive videos. But it's exactly the same technology where you replace pixels by atoms in a way to generate molecules. And so there you can build very interesting generative models for molecules. These could be molecules for drug design, but it could also be for, materials design of many sorts. It could be semiconductors for new, chip design, but it could be materials for carbon capture, but there's many more materials. So that's one class. The other class of machine learning models that's very important is optimization tools. So you can use reinforcement learning or Bayesian optimization or MCTS, or all these kinds of smart optimization tools that need to use evaluation as little as possible, but still produce good candidates for evaluation. So there is a lot of machine learning. Call this maybe reinforcement learning type of machine learning challenges. And then there is, on the more chemical side, there is things like force fields. So there's very advanced force fields in chemistry, which basically means compute the forces that are acting on the atoms to determine how the molecule vibrates or moves or wiggles or folds. And people have been developed sort of, you really need to do quantum mechanical calculations because it's the electrons around the molecule which really determine a large part of those forces, and you can really do this only with severe approximations called DFT, density functional theory, but still that's very expensive to do these calculations. So people have developed these machine learned force fields that predict the outcome of one of these quantum mechanical calculations. So that's another really interesting challenge. And then there is sampling problems. So how do you sample, molecule, let's say how carbon would bind into a particular material for carbon capture purposes? That's sort of a sampling problem. And again, machine learning methods can help accelerate those types of problems.
I'm actually curious, especially because also your background, your PhD was in physics, you moved to machine learning, and now this like molecular science. What advice and insight do you have for people who wants to move between areas of research now, especially with these kinds of new science that comes up with the new potential that's there, and people with maybe the old-fashioned backgrounds of NLP and computer vision who wants to join? What sorts of skills do you think they should develop, and what advice would you have for them?
Yeah, it depends a bit on where you are in your career, I guess. If you're still very early in your career, you can certainly take courses if you want to learn quantum mechanics, you should do it early on in your career, not late, because it's hard. And the older you get, the harder it is to learn difficult things. So I would say take these courses now. If there are even curricula which are mixed between, AF for science or science and machine learning, then that'd be ideal. If you're a little bit later, I took the step, basically. I went from physics to machine learning. So I think you can try to take that step and just try to do a postdoc maybe in that particular field, if or join a startup or a corporate, but ask to work in that particular field. So there's different ways in which you can make the step. But yeah, so it's not always easy if you're in the middle of a career, but it's if you're excited by it, it's definitely worth it to try.
How often do you actually in these this company, but also the previous work, do you get to work with people with completely different and new backgrounds than you or what you are used to?
In a company like, I guess when I was working for Qualcomm, these were mostly engineers in wireless communication, which I thought was also fascinating to think about. So that was a very different field. So the benefit of being in machine learning is that you have access to a hammer that many people need to hit their nails, right? And so if you're interested in interdisciplinary research, you can find collaborators in many different fields who are very excited to work with you, right? You can go to healthcare, biology, physics, chemistry, all of these fields. People really like to work with you because you hold this this hammer and they need it. So yeah, so in I sort of my most recent one is biology and chemistry, and I really enjoy working with domain experts, right? So you have to have the patience to work with domain experts in a completely different field. They will have to learn your language, you have to learn their language, and sometimes it really takes some time to really create a common understanding of how to communicate with each other. But it is a lot of fun if you like these other fields.
And I imagine the outcome of these different points of view would also be quite impactful.
Yeah, so a lot of action happens at the interface of different fields. So people looking at a problem from different angles. I think it's always good to build teams that are diverse in the way that people think, but also diverse in their backgrounds, both scientifically or culturally or something like that. So it's very good to find people who differently think about certain problems, and that's where a lot of synergy and a lot of action happens, I think.
Yeah, nice, thanks. And so I did also want to ask a few questions about you as a supervisor and how you work with young students at university, but also in other capacities. So one question I have is how did you, or right now also usually decide on what topics to work on with your students? Whether it's like a long-term or short-term topics.
Right. So I think supervision is a bit of an art, and the first thing to say is it's different for different students. So some students like a lot of supervision. Some students are very independent, and I think one needs to acknowledge that. I think it is very important that let's say I'm not talking about more or less about a PhD student, but certainly when people are engaged in research, that people own their own research. So basically this means that you are there to guide them to the right topic, to help them if they hit technical hurdles, but it is them that need to, finish their research, and they need to feel that they own what they did. It's not, so it's very bad if you own it and they would be sort of the slave, let's put it badly, but it's like somebody who is doing the work on the side, but you push the research. You can have your own research that you really like, but I think it's important if you work with students that they push the research and you're in service of them, nudging them in certain directions. And that gives a sense of ownership and motivation. I think that's really important. Now, about choosing a topic, I think that's really critical. And I think sometimes I think people pick it too quickly these days. And the way they do it is they go to a conference and they see the hottest topic, they say transformers, and then all want to work on a transformer because they see a tiny little piece of that they would be able to do better. And then they write a paper about an epsilon small change to that particular architecture. I think that is, you can probably get a PhD doing that, but it's not the most exciting thing to choose your topic. If you're a PhD student and a postdoc, you have the luxury of spending some more time of really thinking deeply about the problem that you want to solve and taking the time, and that's where a supervisor is really important. So take the time to discuss the topic that you want to work on with your supervisor and really find an exciting direction, because you have the opportunity to change a complete field. You can actually, if you choose the right topic, you can change the field completely in a different direction. And that's really what you want to do, I think. And so for me personally, I think I have sort of, I don't know, it feels like it's a deep intuition about what I think is an exciting direction to go into. And it's often a little risky because I don't even know whether going in that direction is going to bear fruit soon. And so that's could be a little scary sometimes for students because they might not publish for 1 or 2 years before this thing is taking, becoming to sort of grow fruit. And so for some students, it's better to write papers early and maybe follow the path of less risky research. But for some students, they could actually take this more risky path. And I've had some recent students who I was working on problems that were much more risky, or still risky. So for instance, one topic was traveling waves in, the role of traveling waves in the brain and in machine learning, right? Okay. I feel extremely excited about things like this internally. I feel that's the way in the long run is going to pay off. Or maybe the role of quantum mechanics in machine learning. Could there be a way in which we could use quantum mechanics in machine learning? Very risky, very unclear whether it's ever going to pay off. Now I'm very excited about the role of non-equilibrium thermodynamics in machine learning. So I have a very deep passion for that topic. Whether it's ever going to pay off, it's hard to say. But I do think following these kind of intuitions is important because you can actually move a field.
Mm-hmm. And as you said, it's probably a balance depending on also like the students. But I'm very glad to hear that. I think it is important to work on just these maybe more obscure areas that's how the jumps also sometimes come from in research fields. And you did mention working on papers that change the field, and you have done that at least a few times. I was wondering whether at the time that you were doing that, so for instance, with the graph neural, the graph convolutional models, were you, could you predict that this is going to, like how impactful this can be?
No. So that's the weird thing about this, right? So if you would be able to predict that, then of course you would, always pick these topics. But it's more like when you're working on it, you feel a sense of excitement to work on it. And I would have not predicted that the VAE would have the impact that it had, or graph neural networks, it had the impact that it had. I guess with equivariant models, I had a sense that this would be important. And strangely, that's a topic that took a while to take off because it was rather technical. I should also say that these, as I said, these topics are driven by the students, right? So it's the students that actually did all the hard work, and many of the ideas came from the students. I did just nudging in the background, and I guess I was a partner in, to talk to. But it's very hard to predict whether things will take off. That's for sure. Maybe also going back to what you said about, it depends a lot on the students. So I think when students get nervous about not publishing, it's good to have a mixed strategy. So be in collaborations on lower risk projects, so you get the papers out, and then maybe spend also some time on high risk projects where you can move a field. And so that's probably the best strategy, I think.
Yeah, nice. Yeah, these are very good advice. And I was actually wondering, especially earlier in your career, can you remember a particular good advice that you got that would help you shape what you do?
I can't bring it back to a particular one piece of advice. What I should say is that I have always been very inspired by the people I've worked with, my supervisors. And I can't say that all of them were brilliant supervisors, but I can definitely say that they were all very inspirational supervisors. So, for instance, to give an example, both my PhD supervisor, who was a Nobel laureate in physics, as Gerard at Hooft, and Geoff Hinton, they both were very intuitive researchers, very visual, and both of them said, don't give me all this mathematics, just simple, make it simple as possible, draw a picture or something or an intuition, but the mathematics will come later. And they both claimed they were bad at mathematics, which was completely untrue. They were both really good at mathematics, but they claimed they were bad at mathematics. And sort of that, when I listened to that, it gave me the courage to think in terms of intuition and not, always come up with complicated math. I mean, I can do math to some degree. I'm not brilliant at it, but I can do some math. But if you give a talk and you start your talk with math, you lose your audience, right? And so you need some courage to spend the first 5 slides on high-level intuition about the problem. But that's what people enjoy most, and that's also the most interesting part about science. So for me, by but because they sort of demonstrated by being who they were deeply inspirational to me, and it gave me courage to also be like that. And I think that's the role. I mean, it's similar for a parent, I guess, as for a supervisor, right? You lead by example in some sense.
And I am friends with many of your students, and they do all say the same about you. So I think the fact that this very much like being inspirational and your intuition, which helps a lot. Yeah, thanks. And so you did mention about being bad at math, which I don't think that's true. But I was actually wondering, so how often do you actually do that right now? So coding or going through equations yourself?
Actually, equations I'm doing again because I'm writing a book. So I'm writing this book on thermodynamics, stochastic thermodynamics and machine learning, which forced me to go back to equations and do all the derivations. And that was so much fun. So after I quit Microsoft, or resigned from Microsoft, I went on a trip with my wife to Italy. And every morning I would do derivations and write in my book. And then in the afternoon, we would go hike. And when I was at Caltech for 2 months, I could also do a lot of math stuff, and that was fantastic. Now, coding, I try to find the time, and my people around me joke that I still code in MATLAB, which is like when I grew up, we all coded in MATLAB. It was so much fun. We all had these tricks where how can you speed up MATLAB by vectorizing everything, and I sort of missed the train on PyTorch and all these things. And so when I code, I still code in MATLAB, which really feels like a dinosaur at that point. So not too much coding at this point, but I definitely do math again, and that's really enjoyable. Yeah, that's fantastic to do.
Yeah, that's very interesting to hear. And so about your book, so what is it actually about? What can you tell us about this?
Yeah, so it's of course very dangerous to talk about a book because you commit on public to finish it. But I actually, so this came out of, I did 3 weeks of teaching in South Africa in the African Institute for Mathematical Sciences in Muizenberg, which is actually a Dutch name, but it's near Cape Town. This was really fantastic. And I came there basically with an idea. I had worked a little bit, during my trip to Italy, but I basically hadn't prepared anything. And then in the morning I would teach, and then in the afternoon and the evening I would prepare the lectures for the next day, and I would write in the book. So that was basically, that course was on how to the deep connections between machine learning, and in particular sort of evidence lower bounds and free energy, variational free energies that are being used when you do probabilistic models in machine learning, and the idea of a free energy and diffusion models in machine learning. So it turns out the diffusion model is literally an implementation of a nonlinear, a non-equilibrium thermodynamic system, where you can think of, you start with an image, it's out of equilibrium, you let it diffuse to sort of a Gaussian blob, and then it's in equilibrium, sort of follows the second law of thermodynamics, and then you sort of track that change, and then you try to undo it in the other direction. So you basically, what happens is you monitor an egg that's falling on the ground and increasing entropy, and you try to construct a system that can take an egg that's on the ground and turn itself into an egg in your hand, right? Going against the sort of second law of thermodynamics. So that's what a diffusion model really is. And you can make those connections between the physics of that and the machine learning part of that. And in fact, the paper that was written by Jascha Soldikstein and collaborators in 2015 already mentioned the name non-equilibrium thermodynamics there. So they already were inspired by that. But I think there's a much deeper connection between physics and machine learning. And of course, it's a lot of fun with my mixed background, a lot of fun to try to sort of explore that. And so we're writing a book. I'm doing this together with 2 students, Cyril, you and Lars Holdijk, we are finishing that book. We already have an editor, so it's going to have to be finished fairly soon.
Nice. That sounds great. I look forward to check it out. I do want to also ask about, so we talked about a lot of really exciting topics that you are working on right now, and maybe would be good for people to work on. But if there are some topics that you think are like completely overlooked right now, and there are not enough attention, and you mentioned this, like finding that areas that you are passionate about that no one is working on. But is there any topics in particular that you think would really help if people work on it a bit more?
Yes, I have two. Now I'm really, talking about things that I'm personally very excited about. But I think so. So this thermodynamics is, I think there's a much more in there than just diffusion models. So I think so that's this stochastic thermodynamics relation with machine learning is a very interesting one. The other one I can tell a little bit more, which is work I'm doing with some neuroscientists, as well as my former PhD student, Andy Thomas Keller. So that's about thinking about the role of dynamics maybe in and traveling waves in representations in neural networks. So the way we think about it is, so if I need to, so a human or animal tries to predict the future state of the world all the time, right? Because that's if you know the future, you can sort of anticipate things. And so what you do is you take all your sensory input and you turn this into a representation in your brain. And then in your brain, you simulate how the future would look like. And then if it corresponds with the actual future, then you're happy. If it's not, you have a learning signal. And then you can think about, okay, the way that this dynamics happens in this latent representation in your brain. How would you model that? And so by using ideas from equivariance, basically symmetries, as well as ideas from sort of thermodynamics, which is basically how representations can move in media. So how would a liquid, traverse or move itself? So you can think of these latent representations as liquids where waves are created that sort of travel in these latent representations. We were able to do really well in predicting future states. And that's kind of weird because why would traveling waves be good for that? And that's something that nobody really looks at, I feel. People don't really think about traveling waves in latent representations. And what we found was that these kind of representations are really good at holding memory. So you can sort of encode something in a latent representation, and then this information starts to travel around in orbits, and then you can hold something in memory like that, and then later when you need it, you can just look up that information and decode it back into an answer. And it was amazing how much better it could hold these things in memory than normal RNNs, for instance, recurrent neural networks. And yeah, and then we also found that these traveling waves are really ubiquitous in actual neuroscience and actual brains, biological brains. So there's this mystery that there's these waves in brains. People don't really know why they're there. Do they have a actual function or not? And we can model them well in machine learning models, and they seem to be good for something. And so now there is this really interesting thing happening. Can we? And so I predict many new and interesting discoveries will be made, and maybe we can build better transformers with these traveling waves, or I think many different interesting developments will happen in this space.
Yeah,
so I guess maybe what I also want to say is work with neuroscientists. So I think neuroscientists have really clever ideas, and so that they're observing how the brain works, and there's a lot of clever ideas there that can be leveraged in machine learning. Also, for instance, for energy efficient computation.
Yeah, that's very fascinating. Yeah, I did also wanted to ask whether you still read physics papers, but I guess all of
I
these
do.
topics kind of answer that. But yeah,
I do.
so
Yeah.
how and like, do you think that's really like when you move in between research fields, like how important is that to keep in touch with different fields?
It depends a little bit on your taste. So I have this background, and so somehow I understand the language, and and for me it's interesting to read. I think there's a lot of really smart ideas in physics, and so learning from those, like equivariance and symmetries, really is something that's been developed in mathematics and physics already for many years, right? And so importing that, was a lot of fun. Of course, the same thing happened with MCMC and Hamilton Monte Carlo algorithms which have been used, and there's belief propagation, which were methods which were developed already in physics, and now there's this non-equilibrium sort of systems like this diffusion methods, which are also important for physics. So there's so many interesting ideas that have been already developed in physics, and interesting to see if we can, use some of them in machine learning. So we are working with Miranda Chang and Matisse Gerdes, which is a PhD student, and Miranda Chang is a professor at UVA in physics department, on whether we can use renormalization group ideas in machine learning. Now, so it can be very practical that way. I also have this, but I don't want to publish about it, but I also have this, interest in very exotic topics like the mysteries around the measurement in quantum mechanics. And nobody really understands what a measurement is in quantum mechanics. And it's so weird because this is one of our best theories, the most precise theories that we have, but at a fundamental level, people don't understand the theory. And so, it's almost philosophy to read about them. What is a wave function collapse? And some people even say that, every time a decision can be made, the universe splits into two copies, and you're sit in one copy, and a copy of you sits in the other copy. And this is really serious, right? Physicists think about these things very seriously, and to me, it's completely outrageous that you even consider, that at every instant the universe, gets into a copy. So there's been gazillions of copies. But this sort of almost philosophy, and I find it very interesting to read about these things, although I don't think it will be useful for machine learning at all.
Well, I do hope if anyone is gonna do anything on that, I do hope you get a chance to do. It sounds very, very interesting. Thanks. So there are a lot of questions and comments also in the chat, and I do want to go through them. So maybe we can just do like a quick round of checking what's going on in the chat. So the first question, Milan is asking, what kind of data do you deal with in your day-to-day life in environmental science? Is it all tabular, or is it data in other forms included?
So I've mostly worked on sort of image data and text data, and recently more about molecular data. So molecular data is more like, I would say, a graph structure. So you basically have positions for every atom. You know who is bonded to who. You know the type of the atom, and you need to predict certain properties of these atoms, like the ground state energy or polarization or something like this. In PDEs, you would have as input, at sort of a voxelized grid, let's say around the Earth, you would have temperature, pressure, wind velocities, humidity, all these kinds of sort of thermodynamic quantities. And you want to predict the state of all of these quantities, 10 hours ahead in time or something like this, right? Or 14 days ahead in time or something like this. So yeah, so every problem, I guess, comes with their own types of data. It's graph-like, or it's like image-like, pixel-like, or and then there's the quantities can be either categorical, but they can also be vectorial, right? That means that they would transform in a certain way. Yeah, I guess that's the answer.
Thanks. And maybe kind of related to that, Ferdinand is asking, what kind of models are you most excited about in the context of material science? Transformers or something more like graph neural networks or something else?
Yeah, so I guess it depends a bit on which problem you're trying to solve in material science. So there's these generative models for materials. So there's been some good work already from Microsoft. It's called MetterGen, where it's basically a diffusion-based generative model, where you, as input prompt, you just give some properties that you may want, and then it will generate materials with those properties. So that's basically diffusion-based generative models. For force fields, it's much more like equivariant graph neural networks. And there's many sophisticated versions of that, some of them with transformers, some of them without transformers. Yeah, so those are maybe the main categories.
Thanks. Yusuf is asking, what are the recent advancements that have enabled or could potentially enable CUSP AI's research in AI for material discovery?
Yeah, it's kind of, it's sort of almost the same answer to this question, which is it's these generative models, which are very important, but also RL type search methods. Bayesian optimization, for instance, is one that's important, or maybe like AlphaGo like optimization algorithms, or MCTS methods. And then on the side of the chemistry, there's these force fields which are equivariant neural networks. So equivariance has played a very important role there. Yeah, but these are more feed-forward neural networks. And then I think we also see interesting acceleration in sampling algorithms. So we now have Markov chain Monte Carlo methods to do the sampling, but we have recently actually worked with, maybe that's interesting. So we've recently worked with another student, Jacco Dijkman, and a whole bunch of collaborators on improving something that's called classical DFT, which is a theory of liquids. And then in the old days, so you have to write down some term for the free energy functional, and physicists have written down things there, but it didn't work quite that well. And so we put a neural network there. And this was not a super complicated neural network, but by putting a neural network and learning the neural network for this free energy functional, we were able to improve these classical density functional theory methods a lot. So I'm not sure if that's going to be super helpful in CUSP yet, but maybe in the future.
Thanks. Another question about your work at CUSP AI is from Guillermo. So they're asking, is material design something you can do entirely in simulation? If not, how do you close the loop between the high throughput of AI-assisted design and real-world synthesis and testing of promising candidates?
Yeah, so the whole idea is to bring as much of the sort of the optimization loop to silico. So basically in a computer, but you cannot do everything. So you can try to get as much as possible through simulation, but it's like a funnel. And at some point you still have a list of things that you will need to test. And so it will be very interesting to then work with these robotic labs. So these are methods where sort of, a robot arms fully automatically do all sorts of experiments. And then, so test all these materials, then get very valuable data out of those experiments, and then use those again to improve your machine learning models and speed up your computer simulation methods. So there's an interaction between the sort of the things that are happening in a computer and the things that are happening in a wet lab. Although the trend is going to be that more and more is going to be done in a computer and less in a wet lab. And if it's happening in a wet lab, it's also going to be fully automated. And so the more you can push in a computer, the faster you can search.
Great. And there are a few questions, maybe I can put them together in general, asking about advice for how to learn new, or like get into new fields, or learn new topics, I guess, especially in terms of both like guidance and resources, but also for people. So there are two questions about for people who don't have association with university or research labs, like how to get involved in research.
Yeah, so it depends a bit on your funding situation. I guess if you don't require funding, I think you could try to work, work in a lab basically with some people that would need some help with certain research. So in that process, you will learn a lot because you'll be working with a team, and you get publications. You'll be on publications, which is really important for your career, I think. But of course, they're much more likely to take you on when you don't get paid than if they have to pay. So internships are great. Maybe if there you could be paid, but it's also very competitive space, right? So they typically, take students who are already in their PhD or maybe really talented master students with already some publications. So if you want to start all at the bottom in some sense, it's best to, I think, have other sources of funding and sort of offer your services in some sense to work in a lab, and then show how good you are and hardworking you are, and then and you have some publications, and then from these publications are a stepping stone for maybe getting a paid internship or paid job or something like this. It's probably not so easy if you're not in the system, and unfortunately, to get into it. But yeah.
Yeah, thanks. And so talking about like on the flip side of, so we talked about what to do to be successful essentially. So I wanted to ask you if you can share maybe like a period of time that was challenging for you, or like something that didn't go as planned and failed, and how, like, what was the lesson there for you, and how did you move forward?
Oh, good question. I did have at some point, I was very excited about a particular topic. So this kind of is like, when do you stop research? That's also it's also an art if something isn't working out. So I've had a few, topics that I got really excited about, and in the end, it was all very elegant, but in practice, it didn't work very well. And so, so the question, for me is always very hard. Is it because the idea was bad, or is it because the student couldn't get it to work, and I should try to get another student to also help out? In the end, for this particular one, I think the idea wasn't good enough for this to actually work. And so, yeah, so the challenge is then how to roll this back, right? So, you now have a student that might have spent like half a year on something that didn't work, no publication. And then the question becomes, how do you help that student to be successful anyway? So that I think is very challenging. Sometimes you shoot, and so that's why I think having a mixed strategy is good. So if you don't put all your eggs in one basket, at least some of them will still produce papers. But and some risky ones might not work, right? That's the thing of taking a risk. Sometimes it doesn't work the way you plan it to work. So
yeah, I'm selfishly very glad that you said that, because that also happened to me. So it's good to hear that it happens to the best of us as well.
Yeah. So the thing is, you never hear about this, right?
Yeah.
It's like everybody only shares their success stories all the time, but you can be assured that it happens to everyone. That's for sure. Yeah.
Mm-hmm. And maybe just like building on top of that, so what do you think would be, in general, like no matter the stage of like a newcomer researcher to like a more senior researcher, what do you think would make a researcher better? Like if you want to have like some sort of advice, just trying to like to how to improve as a researcher, as a like an, I guess, as an attitude of a researcher, what would you recommend?
Okay, so humility I think is important. I think there's too many large egos in this field. And so, because if you are humble, you're open to listening to what other people have to say, right? If you are very certain or think you are very certain about everything, you close up. You don't listen to what other people have to say. And so knowing your own limitations and knowing that there are so many other smart people out there that know things that you don't know and you can learn from, I think is incredibly important. In terms of a good researcher, I think seeking out collaborations, working with others in a team, I think is quite important, especially in startups, actually, in companies. Working in a team is incredibly important. I guess as an academic, you could be a loner and doing great work. But it's sometimes a lot more fun to work in teams and work with others. So having that capacity to work well with others and listen to others, be inquisitive about people with other skills and other knowledge of different fields. Yeah, I think also trusting your intuition is not easy. So that requires some confidence. So you need some confidence to trust your intuition. But I think for some strange reason, our intuition is incredibly powerful, and it's a different mode of thinking than we're used to in academia. We're real very theoretical and sort of rational about things. But if you really read about the greatest ideas in science, they were all coming at very strange moments, right? People who were, whatever, under the shower, walking, doing a hike in the forest, and they came at very strange. They suddenly appeared in somebody's brain, and so that and then you have to try, or maybe for me, the best time to think is 5 or 6 in the morning. I wake up, and then I'm in some kind of twilight zone where I just think about things in a very free way. And that's beautiful because, you're not, you don't have to do any math in your brain. It's just like you just feel sort of the intuition. You're very close to your intuition at that point. And of course, many of these things turn out to be bad, when you actually, do your due diligence and scrutinize it. However, some of these things often, are very, very good. There's a kernel of wisdom in what you're thinking, and you just have to find a way to actually make it into a good idea. So trusting your intuition or learning to trust your gut is also something that I think we don't learn students at all, but it's actually very important.
Yeah, I love that. Yeah, thanks. I did also wanted to ask if you can share your typical day-to-day, I guess, waking up early in the morning and start thinking about problems, but just in general, like how do you manage your time working on multiple projects and very different topics?
Yeah, it's actually quite challenging, I think. I get way too many emails and I spend too much time doing email, and that takes away time from other things. And that means that in the evening or in the morning, you're doing these other things, which is not very good for family life sometimes. So again, you have to be a little bit disciplined about these things. So one piece of advice I give my students when they complain, or actually my colleagues when they complain about this, is to say, religiously in the morning, don't look in your email. Make yourself a very nice cappuccino. Don't look at anything. Take a piece of paper and for 2 hours do nothing, then think about science. And after those 2 hours, you deal with all the mess that you created by doing that. You have the rest of the day to fix it. But take every day the first 2 hours. Don't plan anything in there. No meetings there, right? Be religious about it. And then at least you have 2 days, 2 hours a day that you can really think about real science. If you lose that, you become a manager. You basically become a machine that answers emails all the time. And yeah, it's hard. It's hard, but that's, I think, the way to do it. I try to make time, but in all honesty, my life has come to a point where that strategy is almost impossible. And I just do my science in the evening and in the weekends. So my kids are out of the house, so I have more time now to spend some time in the evenings and in the weekends to do that.
Yeah, I like that. I'm actually going to try to implement that. I do have a 2-year-old at home, so I don't know how it works with like trying to focus in the mornings, but that's definitely a very good advice. Thanks. So I want to look back to what we started earlier about your current passion and your current work, getting AI to work for humanity and for good use. What is so like the focus on carbon capture, that's really impressive. What other areas do you think is there for people to work on that are practical enough, that are like close to really being applicable in real world scenarios?
Right. If we're talking about AI for good, right, for societal good. Yeah. So I mean, if you just have to figure out what are the things I worry about most, and then tick them off and see what are there research projects to deal with them. So I think things that are incredibly dangerous these days is influencing people through AI and social media, right? So the fact that we are very malleable, we are very easily influenced by social media and things on television. That's how we are, right? We when we form opinions, we do this in a social context, and unfortunately, these things can be gamed through the social media because we spend so much time on screens. So I think that could be a real problem for humanity. People getting addicted to gaming, or people being influenced to vote in certain ways or to think in certain ways. Polarization that's happening on social media. So I think coming up with ways to measure that and then try to to define sort of policy or laws to battle it, and then and inform politicians about it. I think that would be incredibly important, because politicians are very ignorant about how AI works, and how what the dangers are. So there is a role for us to inform them how to avoid some of the big dangers that are lurking behind them.
Mm-hmm. Yeah, that's very true. Thanks. Unfortunately, we are at a time. I feel like the hour flew by. I really appreciate all of your sharing your experience and your insights. And I think this is really very valuable. This is just the side of a researcher, especially an impactful one like yourself, that we don't see as every day. So it's really valuable to share. Is there anything that you want to share as last words with our audience?
Well, I want to thank you for a wonderful conversation. It was really nice talking to you. And I want to encourage everyone to pick the research that they're most excited about. And hopefully that's something that helps society forward. And I think there's wonderful topics and opportunities out there to align your interests with with societal good. So I hope everybody listens to that inner voice.
Yeah, amazing. Thanks again for joining us today. Thanks from all of our audience, and thanks to the questions also from the audience. And yeah, I hope you get to enjoy this lovely weather that we have in Amsterdam, in Boston as well. And have a good day. Thank you, everyone.
Thank you, Maria, and bye-bye, everyone. Thank you for the interview.